So, surface integrals. So, the book starts out by just talking that, by saying that the relationship between surface integrals and surface area is much the same as the relationship between line integrals and arc length. As you remember, when we first found line integrals, we found them with respect to arc length. Here we're going to assume that we have a function of three variables over a domain that includes a surface. Okay, and what we want to do here, is the following. Okay, so let me just go to the next page here. Okay, so again, we come back to the idea that we can scratch out a surface in three-dimensional space with a vector r that's a function of u and v. As u and v vary, the vector moves, and it can actually scratch out a surface. So that's why we say a surface is represented by a vector function of two parameters. And what we're going to do here is we're actually going to take we have this function, and well, let me just show you right here. We're gonna take a function, okay, a function of x, y, and z, and for every value of x, y, and z, we're going to evaluate the function, or I should say, for a sample of coordinates x, y, and z, we're going to evaluate the function, and then we're going to multiply that function by the area of a patch on the surface. That's that delta s sub ij. So if you recall, for when we learned about line integrals, what we did was we took a function values and multiplied each function value by an arc length, a piece of arc. Okay, and now what we're doing is we're taking function values and multiplying each function value by the area of a patch. And let's see. This is figure 1, which gives you an idea here. Maybe I'll have to make that a little, hold on here. Try to get that a little bit better for you all. Yeah, so you have the vector function r. It's a function of u and v. As u and v vary, the r traces out a surface s in space, and that surface s is shown right here in front of you on the screen. It's figure 1 in the book, and there's the ijth patch of the surface. So interestingly enough, what we want to do is we want to take the function values and multiply them by the patch areas, the areas of the patches. And as we increase the number of coordinates that we evaluate the function at, we multiply that each function value by the area of the patch that it's near. Okay, you can see that here in the figure. Okay, the p sub ij. Okay, hold on, the p sub ij, and which is the point, the coordinate, the xyz coordinate. You evaluate the function at that coordinate, and then you multiply it by the area of the patch that surrounds that coordinate. But as we increase more points, the patches are going to get smaller and smaller and smaller, and we're going to take the limit of that Riemann sum that you see right here. And if we take the limit of the Riemann sum, okay, if we take that limit, we'll get what's called a surface integral of the function over surface S. Okay, and this is known as a surface integral. See how on the left side it's a double integral because you had a double Riemann sum, and you're integrating with respect to surface area. That's a capital S, d sub s. You're integrating with respect to surface area. Okay, so all right, this is fine. Conceptually, we can see what we're trying to do, but if we want to evaluate this, we need to convert this surface integral over our surface S formula into a usable formula. So again, what we can do is rely on the fact that the area of the ijth patch here can be found this way. And you've seen this before back in section 12.6. Okay, if you think about the area of the ijth patch, you can approximate that with a parallelogram. The parallelogram has you know, two tangent vectors at a point that create the parallelogram. One going in the direction of the u direction, the other going in the direction of the, well, I want to say it the right way. One of the tangent vectors is with respect to u, the other tangent vector is with respect to v. And those two tangent vectors form a parallelogram, and the parallelogram approximates the area of the ijth patch. Now, how do we find the area of that parallelogram? Well, it is approximately equal to the cross product of the tangent vectors, the two tangent vectors, and then we scale it by multiplying by delta u and delta v, so we can decrease the size of the parallelogram, you know, well, we decrease the size of the patches and then the approximating parallelograms, so we can get a very good approximation. So you saw this back in section 12.6. And so what we're going to do is replace the delta S up in this formula here with that approximation. So if we do that, then we will find that, of course, the two tangent vectors R and U are right there, right? You know how those are defined. The derivative of the R with respect to U and the derivative of R with respect to V. And again, just so we don't lose focus here, you know, here was the formula for, I mean, this was our conceptual idea of a surface integral. But then how do we compute the surface integral? Well, we approximate the delta S sub ij, that's the area of the ijth, surface area of the ijth patch. I mean, the area of the ijth patch is the surface area, right, of the ijth patch. And that area is approximately equal to the absolute value of the cross product of the two derivative vectors, r sub u and r of v, multiplied by delta u, delta v. And so what happens is then, when we replace the delta S sub ij here in Formula 1 with the approximation here in highlighted in the box there, delta S sub ij, we come up with the formula for a surface integral. Okay, we come up with the formula. So of course, the x, y, z now, your parameterization is going to be using the u and v variables. So you're going to replace XYZ with the, that's a point, but that point is can be found by then the parameter vector R of U and V, right? Because every coordinate XYZ is a point on the surface. And so it can be described by R, the vector R of U and V, with respect to some U and some V. Some parameter U, some value of U and some value of V. Okay, are there any questions on this? Okay, well then let's proceed on. So they mention in the book, well, they say, of course, that the surface, we assume the surface is covered only once as UV ranges throughout D. And they mention that the formula that you see there for the surface integral can be compared. You can see it's analogous somewhat to the formula for the line integral with respect to arc length, right? It's analogous, and it's really absolutely beautiful what you're seeing here. Are there any questions on this? Okay. I'll tell you what. Let's go ahead and let's do an example here. Okay, let's do an example. So let me, should have it right here. Let me give you a moment to copy this example down. Now there are examples in the book. This example is not in, it could be like in your homework, but it's not one of the examples in section 13.6 when you read the material. I wanted to do a different problem with you, one that I thought might, that a little guidance would be helpful for. And that reminds me, class, while I'm at it, I'll just mention this. In, hold on here. In section 13.3, the very last exercise in WebAssign in section 13.3, I'm going to share with you a document that will help you, that will essentially give, the document I'm going to share with you corresponds to exercise 36 in section 13.3. And it'll be solutions to exercise 36 in section 13.3. And using those solutions, then it will help you do the last exercise from your homework for section 13.3 due Thursday. So I won't forget. I'll probably post that in Blackboard and email you when that's posted. Okay, just thought I'd mention that. But let me let you copy this here. Very good. Okay. So we're computing this surface integral over surface S. But this surface S is, well, it's a surface that consists essentially of three connected surfaces. A cylinder, a plane z equals 0. Well, I want to be careful. It's a cylinder together with the top and the bottom disc. So it's a closed cylinder. Okay, a closed cylinder, but the cylinder consists of like the top and the bottom of this surface and the cylinder part of the surface together make one closed surface, like a Coca-Cola can. Okay, all right, and you want to compute the surface integral for this Coca-Cola can. Now, there are three surfaces that make up this Coca-Cola can, right? Or Pepsi can. So how many surface integrals are we going to need to compute? If we want the full surface integral, and the surface integral and the surface consists of three separate surfaces connected together, how many surface integrals do you think we'll need to compute? That's right, Robin. And Robin, once we get the three surface integrals, what do you think we'll do with the three surface integrals once we get their values? Add them up. Exactly right. That's right, Robin. That's right. Just like with line integrals. Line integrals, if you have a path that, you have like a line segment, and then the lines, and then, after the line segment stops, and then you go down another line segment in the path, and then you do a semicircle in the path. You got to add up the line integrals for the different uh, uh, curves that make up the path. Same thing with this. Same thing with this. So, okay, let's go to the next page. Now, well, wait, let's also remember, too, what we have to do here. So, remember, this is your formula. This is the formula that you're going to have to use. You're going to have to compute three of these surface integrals and then add them. But in order to compute a surface integral, you need the parameterization of the surface, or of each. So we're going to do three surface integrals, and for each surface, we need to get its parameterization. Okay, so all right, because that's what this formula is based on. R of UV, that's parameterization of the surface, right? Okay, so that being said, let's go back to the thing here. Okay, so we move to the first page. And what I've done is I've drawn our surface. I've drawn our surface here, which consists of S1 union S2 union S3, those three surfaces. S1 is the top disk, S2 is the cylinder, and S3 is the bottom disk. Okay. So parameterization is very important, and it's just helpful. let's see, Eric says since it's a perfect cylinder, can't you just say 2 times x on the top instead of the top and the bottom? No, because a good question. The parameterization of the top disk, okay, will be different than the parameterization of the bottom disk. There'll be some similarities, but the parameterization will be different, a little different. And you'll see that. Very, very good question, Eric. Very good question. So, okay, parameterization. So let's start off with the top disk. How are we going to parameterize this top disk? And you know, the top disk, you have to get the inside too. It isn't just, you know, it's a surface, right? So you want this vector R of UV here. You want that vector to scratch out the entire surface S1. Okay, you want it to do that. So how will that happen? How will that happen? Well, so first of all, the cylinder, the top of the top disk is has z equals 2. So you know the parameterization here for the top disk, you have an x, you have a y, you have a z component. Well, the z component is 2 because the disk is 2 units above the xy plane. Now, to get a cylinder, right, to get a circle, you multiply, you would have for x and y, you'd have the cosine of u and the sine of u, right? I mean, you're pretty familiar with that. But again, we're not just going to get let me see here. We're not just going to get a circle of radius 3. We have to get you know the entire surface, and that means the inside of the surface as well. So to do that, we have to have a v as like a radius. It acts as a radius, that parameter, and v goes from 0 to 3. So if we let u go from 0 to 2 pi, that'll get us circles. And if we let v go from 0 to 3, that'll change the radius of the circle. So the biggest circle has radius 3, and the smallest circle is just the point in the middle, right? Are there any questions on the parameterization? Okay, all right. Well, now, you know, that's kind of the hard part, is getting the parameterization. Now we just apply the formula. So the formula says that we need to compute the derivatives with respect to u and v of our vector function. And I do that here. Of course, the derivative of the vector r with respect to u, we hold the v constant, right? We hold the v constant. And if we hold the v constant, the v stays there as it's, and then for the derivative of the parameter vector, or of the vector r with respect to v, we hold the u constant. And so that will be our derivative vector. And now all we need to do is get the cross product. And before we go further, I'll mention here that in terms of, you know, the parameters u and v, the domain created by these parameters u and v is just going to be this rectangle, because for every value of u, v goes from 0 to 3. For every value of u, v goes from 0 to 3, and so that's gonna trace out a rectangle. So we're going to need this later on, this rectangle, for when we do our double integral. You know, we need a domain for our integration. Okay, so then what I do is, of course, the cross product here, and I end up getting negative v times the vector k. Let me know if you have any questions to this point. Okay, and let me know when you're ready to move to the next page. Okay, Ryan's good. All right, Eric. Eric's good. Okay, Robin and Naima are good. Okay. All right, so now what we have to do is the formula says we have to find this cross product vector, which equals negative v times the vector k. We have to find the length or magnitude of that vector. And so, okay, that's not too hard. The length would just equal v. And actually, v is positive. Well, v goes from 0 to 3, but we'll note here that v is greater than or equal to 0. So, you know, we can't have a negative length, right? So and it's all good. We don't need to, in other words, we don't need to have the absolute value of v. Well, now we have everything we need to work through the problem. We have everything we need. Okay, so what we do, of course, and let me just hold on here one moment. Now, so the formula is the hold on here. I'm looking at the formula 2, just before example 1 in your section 13.6. And of course, you're going to take the function, evaluate it at the parameter at the vector r of uv, and then you're going to multiply it by the length of the cross product of those derivative vectors. So that all that is right here. All that is right here, right? This the cross product is the length of the cross product is just equal to v, and the x squared plus y squared plus z squared. Well, in the parameterization for this disk, x was equal to v cosine of u, y was equal to v times the sine of u, and z was equal to 2. Okay, and so now you'll notice too. So this will reduce to v squared plus 4 times v, because cosine squared of u plus sine squared of u equals 1, and you got the factor of v squared in front. But you'll notice that I have not committed yet to my integration. I mean, in other words, I know that based on that domain D that I drew on the first page, I know what my limits are going to be, but I'm not bringing them in yet. You know what I mean? I'm not bringing them in yet. I don't want to do too much at once here. I want to, get my integrand in good shape, and then I can bring in my limits. And so now, the double integral of v cubed plus 4v, well, that rectangle I can treat as a type 1 or a type 2 region equally. It's equally easy. I'll treat it as a type 1 region. And then, you just do the integration. You just do the double integral, and you'll get 153 pi over 2. Okay. Now, for now, that just is, don't worry about kind of what that means. You don't need to worry about what that means right now. It's just a surface integral. Trying to think if maybe there's, yeah, it's just a surface integral. Okay, and please let me know if you have any questions. Okay, and when you're ready to go to the next page, just give me a thumbs up, and we'll move forward. Okay, Eric. All right, Ryan. Good to go. See, in a classroom, I would kind of look at you and see if everybody's kind of done copying. But here I have to, I have to do it this way. All right. Maybe one more person. Let me. Okay. All right. Very good, Robin. Very good, Diedoff. So, okay, now we're going to do the surface integral for the cylinder. Okay. So, what do we have to do? Well, all right. We have to parameterize the cylinder. Right. Now, I'll note here. I'll note that the cylinder. So parameterization of a cylinder. This would be, it's a cylinder of radius 3. So x would be 3 cosine of u, y would be 3 times the sine of u, And it's an up and down cylinder, so Z will equal V, and V goes between 0 and 2. But you notice I don't put a less than or equal to here, because the cylinder does not include the top and bottom discs. It's just the cylinder part of the surface. And now it isn't going to matter in terms of integration, but I'm just saying. So clearly then the region D is going to be, I don't have to redraw that rectangle again for region D. And I'm going to do the same process I did for the first surface. We have to find the derivative vectors. We have to take the cross product of the derivative vectors. And of course, we have to find the length of that cross product. Okay, so I'm just going to kind of let you quietly copy things down here, and let me know if you have any questions at all. Okay, and let me know when we're ready to move to the next page. Okay. Okay, Eric, Ryan, and Ryan are ready to go. Very good. All right. Okay, so now we have to apply the formula. We have everything we need to apply the formula. So, again, here's our surface integral over this second surface S2, this cylinder. And for the cylinder, x was -3 sine u. I should have a u here. let's see, y was 3 cosine of u, and z was equal to v. Okay, and so it's just a double integral that I know you can easily do. That's why I didn't show the integration part. And when you work it out, you'll get 124 pi. Are there any questions? All right. May I go to the next page? Let me know. We have one more surface that we have to do. We found the surface integral for the top disk. Okay, we found that to equal 153 pi over 2. We found the surface integral for the cylinder, okay, which is the, lateral side, the cylinder. Surface integral is 124 pi. And now we have to find the surface integral for the bottom disk. All right. Okay, then let's move forward then. Okay, so here's the bottom disk. Okay. And of course, it contains the origin. The parameterization is just like the top disk, except z equals 0. See, that's the difference. That's why you can't, you can't use this. It's a different parameterization. It's a different parameterization. The top disk, z was equal to 2. The bottom disk, yeah, z was equal to 0. And so, but of course, the v cosine u, v times sine of u are the same. And we can show that the cross product would equal negative v times k, and the magnitude of that cross product vector, the length of that cross product vector is just v. That should be a v there. Hold on. Okay. And so again, we just go after the surface integral. there any questions? All right, let me know when we're ready to go to the next page. Okay, Ryan's ready to go. Okay, very good, Ryan. Very good, Eric. Okay. So then this surface integral, you'll compute it to be equal to 81 pi over 2. And so then what is the value of, so that, that's the value of the surface integral across the third surface. Now, for the entire surface integral, since the surface S is equal to the sum or union of those three separate surfaces, to get the surface integral over the entire surface S, which is that closed cylinder, it's a closed surface, okay, we just add up the three surface integrals for over surfaces S1, S2, and S3, and when we do, we're going to get 241 pi. Okay, let me know if you have any questions, please. And I appreciate all of you are here. I noticed we lost a few students. About 3 students left early. I don't know why, but class goes to 8:45. Multivariable calculus, we got to stay strong, right, until the end, right? And really, you're getting in the most important material of the course is the material you're learning now, because it has tremendous applications And you'll see it, I'm sure, in future classes, like engineering physics classes. And it just shows you why everything was worth it, what you've done, you know. Now I want to make one comment after this example, one quick comment there's a comment in the book I want to just briefly mention. So once you're done copying this, let me know and we'll go to the book. How many are feeling reasonably good with the surface integrals so far? Who's feeling reasonably good? Okay. Good, Ryan. Good, Eric. Good, Robin. Yeah, they're a little long. Yeah, well, the trick is getting the parameterization. Good, Ryan. That's really, you know, and that's actually what I wanted to mention. Wanted to make a comment on that. Okay, so are we good? May I go? May I move forward into the book for a moment? We're all good with this example? Just give me a thumbs up. Okay, Robin's good. Good. Ryan, wonderful. Dan, excellent. Eric, excellent. Okay. Okay, so in this problem that you've just seen, for each surface, we found its parameterization. And we used the fundamental formula, the formula 2 from the book. But if we look in the book here, okay, they talk about, well, what if you have a graph? In other words, what if z can be thought of as a function of x and y? If you have a surface S that can be written as z is a function of x and y, then the parameterization could be, you could let x equals x, y equals y, and z equals a function of x and y. And then you could, you know, find the derivative of the vector r with respect to x, the derivative of the vector r with respect to y. That would be what that is right there, because, well, it is. It would be, right? If you do the cross product, of those two derivative vectors, you'll get this cross product, okay, and the magnitude of that, the length of that vector would just be equal to the square root of the partial of z with respect to x squared plus partial z with respect to y squared plus 1. And so then the formula for find the surface integral formula could be expressed like this formula. But this only works if z is a function of x and y. So it's a nice formula, you know, kind of maybe easy to use, but it only works when the surface z can be written as a function of x and y. So like, for example, the cylinder surface, that could not be used. This formula could not be used. So I recommend really that you try to use the original formula that we used in the example and try to get practice with your parameterizations of the different surfaces. That's what I wanted to say. Okay, I'll stop there.